Now, in the case of a buck converter, we can see that the current ripple as a percentage of its output current can be represented as a function of its circuit components, that is resistance, duty cycle, inductance, and frequency. Now, from this expression, we can observe that for a very high value of inductance, we'll have very less value of current ripple. That is, if your inductance is reasonably high, then you will not have any ripple in your current. Your output current is going to be almost DC. You can see that in this case, your output current is almost DC. But if your values of the inductances are low, in that case, your output ripple current is going to increase. And there will be a point where your output current oscillates between 0 and maximum value. And if you go beyond that level, then your output current becomes discontinuous. Now, if you want to know the point at which your output current moves from the continuous to discontinuous, is what we call it as critical value of inductance. That is the boundary between the continuous mode of conduction to the discontinuous mode of conduction. So what we call it as L critical. Now, how do we get L critical? Now, we can see here in this particular picture that you have almost a DC current. And as you kept on reducing the value of the inductance, you see that the values of the output current are oscillating between 0 and maximum. Now, in this case, if you look at the amount of the current ripple, you can realize that this is what is delta I for us, and this is what is I naught average value for us. Now, it is very easily understood from this particular circuit that at the boundary where you have the value of inductance as a critical value of inductance, the current ripple, that is delta IL, is almost 2 times of the output average current. So now if you substitute that condition for the case of critical inductance, now you know that this factor is 2 times of I naught upon the value of I naught, because your delta IL is becoming 2 times of your output current when you have value of inductance selected to be critical. So now if you wanted to know the critical value of inductance, then it is R multiplied by 1 minus D upon 2 times of F. So this is what we call it as critical value of inductance, below which your currents in buck converter becomes discontinuous. If you have your inductance values chosen to be critically, significantly higher than this critical inductance, then you can observe your output currents are almost DC. Now in this figure, you can see that when your inductance is exactly equal to critical, then your output current is oscillating between 0 and maximum value of current. But if your inductance value is 10 times of the critical inductance, then you will see almost DC values of the output currents. It will also be understood that if you further reduce your values of the inductances below your critical inductance, what happens is this is what is going to occur. Now, if you reduce the values of the inductances below critical inductance, you can see that the white case where value of L is half of the critical inductance. In that case, your current, white color current waveform, you can see that the current is going beyond that current during the margin, and it is going above that. And then during the off period of the switch, your current is hitting back to 0. So this is what is the waveform that you get if your inductances are low and you have the discontinuous conduction mode of current. Now, how you will get output voltages and output currents in the case of discontinuous conduction mode is that expressions we derived with an assumption that the conduction mode is continuous are still valid if your inductance values are much lower.